Hi everyone, welcome back to Paradise Line. Today I want to go with you deeper into mathematical definition of a 3D point cloud, and also I want to explore it with you several methods of 3D reconstruction. So the first thing to understand is that a 3D point cloud is in fact a discrete samples of a surface. And what is the main challenge is to get a continuous representation of the same surface. So the main difficulty that we have in 3D point cloud, which is represented by vertices with X, Y, Z coordinate, is that we don't have the connectivity information between points. So we need to estimate it. The second one is that we don't have the normal estimation, the normal direction of the points. So in order to solve this challenge, we have several methods. The first one is the convex hull. Convex hull is in fact computing the smallest convex set containing all the points. Okay, so it cannot represent concave features, so such as holes, indentation, and is only useful for bounding volume approximation. Good also for collision detection, initial volume estimation. Then we are going to talk about the alpha shape. When the alpha shape is a generalization of the convex hull controlled by a parameter alpha. The main idea is if alpha is close to zero, then it will return the original point set without any connection. And if alpha is go to the infinite, it will return the convex hull. The optimal alpha will capture surface details without holes. Then Ball pivoting algorithm, that's a BPA. I love this algorithm. Why? Because it's a ball of a radius rule over the point cloud connecting point in if touches. So it starts with a seed triangle, 3 point on ball surface, and then it pivot ball around each edges. When ball touches a new point, then it's creating a new triangle. Repeating that until no more triangle can be formed. So this is the concept of the ball pivoting algorithm. The last one we are going to see is for me, the most mathematically elegant method, which is the Poisson reconstruction. How this algorithm is working is currently computing the gradient of an indicator function x equal to the normal field of the normal. So meaning we are obliged to have the normal estimated from the point cloud in order to use the Poisson algorithm. If you just have a point cloud and you use the Poisson algorithm from Open3D, it will require you to compute first the normals by estimating normals and then to try computing the Poisson algorithm. So in order to solve this gradient indicator function, we need to solve the Poisson equation. And because the Poisson equation is a linear system, we can solve it via octree discretization. So we need to define a depth because an octree it's like a grid. We need to define a depth. In general, it can be 9, for example, and a higher depth will provide more detail but slower computation. Then we will play also with the density. When the density, by removing density from a certain threshold, it will provide a better mesh with more details. The last thing we are going to see together is the normal estimation, because as I said, ball pivoting and the Poisson algorithm needs the normal estimation, the normal information from the points. So how to get this normal estimation? So also Open3D has a build function for that. But the idea from this function is in fact to get from each single point the k-nearest neighborhoods, okay, compute the k-nearest neighborhood to get the points around these points, and then to compute the covariance matrix and to compute the eigenvector with the smaller eigenvalue, the smallest eigenvalue, and this will be the direction of the normal. So let's go ahead with the code. I'm going to share my screen as usual in debug mode. Okay, let's start. Okay, so I'm importing NumPy as NP, Open3D as a 3D, and visualization, 3D Viz, Matplotlib, Loguru, and function for surface R. So we'll see that together now. Okay, so I'm loading the bunny point cloud with 650 points. Let's display it. Our lovely bunny point cloud, okay, with a Poisson disk Yeah, with the sample, sorry, with the sample point Poisson disk for the sampling. Okay, so then the compute convexal. So let's see inside. The convexal is in fact a function of Open3D. So compute convexal information, compute vertex normal for the rendering, and then for visualization, I can also create the line set in red and assign red to that and to plot it in 3D. So we can see this is the result of the convexal, but I currently display only the line set in red without the mesh. Okay, so let's see now the mesh. Okay, this is a match from the convexal. Let's continue. So the alpha values, as I said, the alpha is in fact a generalization of the convexal, and when the alpha will be smaller, it will be with more details, and this one will be very close to the convexal. So let's inside. To compute the alpha shape, we just need to create first thing a tetra mesh, pre-compute tetrahedra for efficiency. It's correlated to the Delaunay also. Let's continue. And then the alpha shape algorithm we take as input the PCD, the alpha value, and the tetra mesh and the PT map. Compute vertex normal, and then we just add the different meshes computed by the different values of alpha in different lists. In this list, sorry. So let's see. So this is the first value of alpha. Let's continue. Second value, and this is the smallest one. Okay, so let's continue. Now I just reload the bunny mesh with more points and then draw it and then compute the ball pivoting information. Also, we need to define the radius. As I said, the ball pivoting start with a seed triangle and then go ahead and it's depending of the radius. So we need to provide just the PCD and the radius values and then to visualize it. And we can see a very well representation of a mesh. Like the mesh, I currently display both mesh and point cloud, and it's very close to the points. This is also the advantages. For example, the Poisson algorithm will not provide such detail regarding the original points. It can approximate and estimate a surface very well, but without going through the original points sometimes. So this is the advantage also of the reconstructing ball pivoting. So the last one, the Poisson algorithm. So let's change the original point cloud from bunny to the eagle. So this is the eagle with the points, as we can see. Okay. And now I'm using the reconstructing. Okay, so first thing, point cloud Poisson algorithm. So as you see, the depth by default is equal to 9, and the density quantile is only to reduce the noise and to reduce the outliers. So let's do it. As you can see here, is currently solving the linear system. Linear system solved with 3 seconds. Okay, let's visualize it. We can, as I said, reduce the outliers by removing from a density threshold. So let's continue. So we can see here the density map. Okay. And now we can see the mesh reconstructing after removing outliers. So we can see that the area with the density, the higher density values are removed. Then the last thing is to compute the estimate normal. So let's go inside. It's only estimate normal, pcd.estimate normal, providing the normals, and we can display that, and we can make it bigger with the plus and smaller with the 9, with the minus, and we can remove that with clicking on N on the keyboard. Okay, so we can see that it's go outside from the mesh, so it's great for rendering in the mesh, in the mesh, in the mesh, and also we orient normal consistent with the tangent plane, meaning we just propagate the tangent plane or all the on all the points to make sure all the normals of all the points will have an outside direction. So that's it for today. Next week, we are going to see together how to learn how to make a model, to build a model in order to learn a 3D representation. That's why we already talked about sine distance function, because in general, to learn some representation, we need to use loss based on sine distance function, and also model with architecture such as unit 3D architecture to estimate a volume from a volume, or also from 2D representation to 3D representation. It will be very interesting. Thank you for following me. Thank you to trust me, and please follow, subscribe to the channel and share. Thank you, and see you.